So welcome you all to today's lecture, that is noise in FM. So if you'll recall the noise in AM, also in that receiver, we have used the separated receiver. Noise in AM and noise in FM, we are using separated receiver. And the second point, if you'll remember that we have modeled this channel as AWGN, that is any communication channel, most of the communication channel in another communication also you are using AWGN channel, that is known as additive wide Gaussian noise channel. So noise is additive in nature, we are assuming. Second point, the probability distribution function of the noise is Gaussian, and the power spectral density of the noise is white. So that's why at the receiver point, so if they look, this is the total is the receiver block, it is separated and receiver block. Already all of you have gone through the separator and receiver. I should not explain the working principle of separator and receiver. Only if you look at here, at the input of this, at this point, the signal which you will receive, that is the input modulated RF signal plus the noise, correct? So in case of separated and receiver, when you learned in the receiver part of a noise, a particular amplitude modulation, there we have not considered this noise part. Now we'll analyze the receiver performance of the separated and receiver in the presence of noise. And here in this input, there are two terms are there. One is modulated RF signal, another is noise. And this modulated RF signal is here in the FM receiver. It is an FM signal. That is frequency modulated signal we are receiving, plus with that we are receiving noise. First, this signal will pass through this RF amplifier. So this RF amplifier will provide you some part of the gain of the total amplifier. Then this part, the first converter of the separated and receiver, there is a mixture and a local oscillator, and this local oscillator frequency is very high, or you can say larger than the FM RF frequency. So that's why many times we are telling this super term comes here, and heterodyne terms comes due to the multiplex, or you can say mixture. Now once we'll multiply this signal, this local oscillator signal, if we'll multiply this signal with these two terms, then there will be frequency translation, because this local oscillator frequency is FLO. So local oscillator frequency will, you can say, is very large than the FRF, or radio frequency, or the modulated signal frequency. So therefore, here at this output of the mixture, we'll get two type of signal, or two type of signal. That is, one is FRF plus F local oscillator, and another is F local oscillator minus FRF, and that is known as the difference between this local oscillator and the RF frequency, that is the carrier frequency of the FM modulator, is known as IF frequency. So that's why you have used IF amplifier, and most of the gain actually of this at the receiver we are providing at the IF amplifier. So once the signal will be at the output of the IF amplifier, then we are using IF carrier filter, which actually helps to reduce the noise power, because the IF carrier filter only allows the bandwidth of the, or you can say the bandwidth of IF filter is only to accommodate the signal bandwidth, okay, the RF signal bandwidth. So beyond that band of this bandwidth of this IF carrier filter, all the spectrum will be suppressed to suppress the noise, because white power spectral density is flat. You can say power spectral density of white noise is basically defined like this. This is purely flat, and this you can say zeta by 2 eta by 2 we are telling, and this is the GNF. This is known as GNF, power spectral density of the white noise. So here, that's why we are writing power spectral density of white noise is equal to zeta by 2. And these three blocks are very important for our noise in FM analysis. Now, from this point, we'll calculate the signal to noise power of output signal to noise power as well as input signal to noise power. So first block, if you look at, we are using IF carrier filter, then demodulator. And here we are using FM demodulator. And then there is a bandpass filter. Bandpass filter after demodulation, if you look at even a bandpass, sorry, this is not bandpass, this band filter. This is a basically low pass filter. It blocks, because it is known as baseband, because it also blocks the DC component as well as the higher order harmonics, and as the frequency component beyond my message signal bandwidth, that will be suppressed by this baseband filter. So input to this receiver, now if you look at this to receiver is basically modulated IF carrier signal, that is now here at the input to the receiver. If you look at before this RF amplifier, the input signal is the FM signal plus noise, and this FM signal frequency is FRF. But after conversion, first conversion, we are getting IF frequency. Therefore, the output of the IF amplifier is FM signal with a carrier IF carrier frequency. So now the input signal power we can say SI, and from this power spectral density we will calculate the noise power, input noise power. And similarly, at the output we will get the signal, which is my baseband signal, which I will recover at the baseband filter. That output signal power is S0, and the amount of the noise which also pass through this all these three stages, that will also appear at the output of the baseband filter, and that noise power is known as N0. So this is all about the super-rated and receiver. Now, what is the objective of noise in FM? So first objective is that we have to find the input signal power, then find the input noise power, then find the output of the signal power, and at the same time also output of the noise power. Why we need this signal power, noise power, input as well as at the output? Because when you are actually evaluating the performance of any communication system, particularly in analog communication system, we are going for the signal to noise ratio, SNR, as a performance evaluation parameter. So that's why the signal power by divide by the noise power is known as SNR. So that's why find the output signal to noise power is our objective. Then also we can, based on the input signal power and input noise power, we can evaluate the inputs SNR. Once we evaluate this input as well as output signal to noise power, then we can also calculate the figure of merit, which is the ratio of output SNR divided by, or you can say ratio of output SNR and input SNR. So the FM signal, if you remember the FM signal, mathematically we can write, if the carrier signal is A cos omega ct and MT is my baseband or information signal, then FM signal can be represented like this: VFMT is equal to AC cos omega ct plus KF 0 to T MT dt. Here this KF is a constant, and it is also known as the sensitivity of the FM modulator. So now if you look at here, in this case the amplitude is constant because AC. So FM signal amplitude is constant, only the frequency of the FM signal varies according to the instantaneous value of the baseband signal. So the instantaneous frequency you will look at, because the frequency is varying. So instantaneous frequency actually is proportional to my baseband signal. So that's why you will calculate this instantaneous frequency Wi, This is nothing but the derivative of this angle. This is theta t. This is the angle. D theta d by dt. If we'll go through this, then I will get omega c plus kf and mt. So the instantaneous frequency is directly proportional to the instantaneous value of the baseband signal. Therefore, we need a device which will produce an output proportional to instantaneous frequency of input to FM signal. So what kind of device we need? If you look at that, device is known as a frequency selective network. If I'll pass, because I am talking about the FM demodulator. So if you look at FM demodulator, then I need a device which actually is basically a frequency selective network, which will give you the an output voltage which is proportional to the input signal frequency, and that is known as a differentiator. Differentiator is act as an FSN, frequency selective network. So how we'll look at that, or how we'll say that this differentiator frequency selective network? Let us see. If we derivative this frequency modulated signal, that is d by dt of fmt, then I can write that this is the FM equation, fmt. This is the FM signal. So here we are going to derivative this with respect to time. If we'll do that, then we'll get a signal that is minus SC omega c plus kfmt into sine of this term. Look at here, this signal, if the FM signal pass through a differentiator, then we are getting a signal that is SC omega c plus kfmt and then sine this term. If you closely observe this, this is an FM signal, but the amplitude of this FM signal, this amplitude part, is not constant. But if you compare this and this signal, it's exactly this term looks similar to the amplitude part of the AM signal. So that's why we can say here that equation 4 is an amplitude as well as frequency modulated signal. So this is a carrier signal, but the frequency is not constant. This carrier signal frequency is not constant because it is an FM signal. And the amplitude of the signal, if you look at, that is, if you remember the amplitude modulation, then this says SC into 1 plus MT, 1 plus MT, 1 plus MT, and then into sine omega ct. You can use a cos omega ct, whatever, there is a carrier term. So this term into, I can say sine, suppose I'll write also sine omega ct. So now this term, if you look at, this is your amplitude modulated signal. Now look at here, this term is equivalent to this term, and this sine omega ct is a constant frequency term, but here it is a frequency modulated signal. So therefore equation 4 looks like, or is equivalent to an amplitude as well as frequency modulated signal. So now if we'll go through the time domain representation of FM signal. FM signal looks like this. The amplitude is constant, and here the amplitude is constant, you can say, but the frequency varies. Frequency varies according to the instantaneous value of the. So it's an FM signal. If you go to the derivative of the signal, the derivative signal of this FM signal will looks like this. And look at here, this is not only amplitude modulation, the envelope of this signal followed the baseband signal, and this, the carrier part, is an FM signal. So that's why this is the differentiated difference, or you can say the differentiation of the FM signal. Now, this signal, what is our objective? Our objective is to get back the baseband signal, and here we can use an envelope detector to detect the envelope. So this diode detector or envelope detector can be used to detect the envelope of the AM plus FM signal. the output of the dye detector is passed through a baseband filter, because if you remember the three blocks, one is IA filter, then the FM demodulator, then there is a baseband filter, and so the output of the dye detector will pass through a low pass filter to recover the modulating signal. So therefore now if you remember the FM, recall the FM demodulator part, so we can change that detector part or demodulator part of FM signal is that input is FM signal, and first block is a d by dt or differentiator block or differentiator with time block. Then it is the output of this differentiator will pass through an envelope signal, because this output is equal to M plus FM signal, and we want to detect the envelope of the uh, M plus FM signal, which are the output of the differentiator. Then once we will pass this AM plus FM signal through envelope detector, it will detect the envelope of AM signal, which is our baseband signal plus harmonics and other components, higher order frequency components. So this baseband filter or low pass filter helps to suppress all the higher order frequency component as well as harmonics, so that we can get back our baseband signal. So these three blocks is the FM detector or FM demodulator. So this block will replace at the detector plant here. In this case, people remember that block, if you remember that block in the superhedron, this demotor block will replace by three blocks. One is differentiator, another is a diode detector, then the already baseband filter is there, so we don't need to add again baseband filter here. So this demotor part will be simply replaced by a differentiator and a diode detector. So now if we'll go through the same point, now look at here how it looks like. Here we'll get this FM signal, then this will be the envelope of the AM signal, and then once we'll pass this through baseband filter, we can get back our baseband signal. When the received signal is FM plus noise, that is, it is a noise FM signal or noise mixed FM signal, then in the presence of additive white Gaussian, this signal will be, now this noise term will be added. So that's why the FM signal plus the noise term NT. So now what will happen? If I'll pass this signal through a differentiator, then definitely the amplitude of this output signal of the differentiator output signal will not follow the baseband signal. So as per the definition, the amplitude of FM signal is constant. However, the amplitude of the noise mix signal is not constant, because now what happens, because of this noise, this constant term will not remain as AC, because it will vary based on this noise term. So rather, the amplitude varies according to the instantaneous value of the noise NT. Therefore, the received noise mixed FM signal can be represented as, we can represent now this as a time varying amplitude FM signal. Instead of AC cos omega CT, this term, instead of this term, because the noise is added to this FM signal, so this term can be represented as, because of this noise NT, the total received FM signal can be represented as AT into cos omega CT plus KF and integration 0 to T MT dt. And this AT is a time varying amplitude of FM signal. So now if we'll go for the differentiation of this signal, because after this, once we'll receive this signal, then we'll pass through a differentiator. So this differentiator, this differentiate this signal, this received signal, which is actually now, this is not the radio frequency. We are always, mind it, we are always here working with the IA frequencies. because we are not bothered about the RF frequency. Once it will convert it to the first mixture, then we are getting the output of the IF amplifier, which is fed to the IF filter. So we are talking about the input to the IF filter is my received signal. So now we will derivative this received signal, which is a noise mixed FM signal, the previous equation. Then this equation will looks like this. Now, if we compare this signal, this to this is our noise. This to this term. If you look at, this is FM signal. This is FM term, and this is not exactly AM term because there is a term AT is multiplied. So now, though amplitude here, there are amplitude are two parts now. There is a AT term, there is a omega C plus K, and this part is my information part or our information part, and this part is noise part. And if you look at this first part is also FM signal, and this is a dAt by dt. This is the derivative or rate of change of the amplitude variation of FM signal. So therefore, if we pass this signal through the diode detector, our purpose will not solve because we could not detect the envelope which is our proportional to baseband signal, or we can say the envelope of this type of signal will not resemble our baseband signal, or it will not proportional to our information signal. So we cannot use diode detector as envelope of equation 3 and does not follow the baseband signal. Hence, it is essential to maintain the amplitude of the noise mix signal constant before applying to differentiator block of the receiver. What is our objective now? Because this differentiator output is not an AM and FM signal. Even if you look at the envelope of this FM signal does not follow the baseband signal. This is because of the amplitude variated FM signal. And why amplitude variated FM signal? That is also this AT is not proportional to only my baseband signal. AT is proportional to the noise. So therefore, we want to what we want to do, we want to fix the amplitude, or you want to make the amplitude of the received noise mixed FM signal a constant. How we'll do that? So therefore, in this case, before passing through the differentiator, what we'll use? We'll use another two blocks. One is hard limiter and band pass filter. And these two blocks help us to make the noise mixed FM signal input noise mixed FM signal to a constant amplitude FM signal at the output of this band pass filter. How it will do? Let us go through the demonstration. First, we will go through these 2-3 blocks as per previous discussion. These 3 blocks will be there. But here, what we are doing now in the demodulator part, we are adding 2 blocks. Why we are adding these 2 blocks? To limit the amplitude to a constant value, so that the amplitude of FM signal will not vary. So now, look at here. Suppose this is the noise mixed FM signal. If you look at here, the amplitude is not constant. The amplitude is varying, but at the same time the frequency, because it's an FM signal, so that's why the frequency is varying. But because of noise, the amplitude doesn't remain constant or to fix to a certain level AC. Rather, it is varying according to the value of the noise at the particular instant. So now, what is our objective? To choke, or you can say limit the amplitude to a particular range. If I limit at this point, so I need an amplitude limiter. So then I will get a signal, this kind of signal. Look at here, the amplitude is constant, but here the frequency is varying, but this is not purely sinusoidal signal. But this is, you can say, because the frequency is very high, it will be act as a rectangular pulse amplitude variated signal, correct? So now, if you choke this using hard limiter, what is hard limiter? Hard limiter is characteristic is VG input and output characteristic of a Hard limiter is looks like this. What is that? This if I'll give input in this side, the output of the hard limiter has two value, either 1 or -1. Only two value I'll get. So two levels. If the input is greater than 0, then I'll get +1. And if input is less than -1, then I will get less than 0. Sorry, if the input is less than 0, then I will get -1. So this is basically hard limiter characteristic, input output voltage characteristic. Now if I use this for this input signal, our noise mixed FM signal, then I will get an signal like this. And this is an, if you look at FM signal, but here it is not look like sinusoidal, it's a kind of a pulse width modulation signal, you can say, or it is a frequency modulated signal. Pulse considering as a pulse as a carrier. So therefore, what we will do now, if you will pass this signal, because if you look at the block diagram of our FM demodulator, we have gone through that. That is, we are using a hard limiter followed by a baseband filter, a band pass filter. So now if I use a band pass filter here, then the fundamental frequency of this FM signal will be passed through the baseband by a band pass filter, and here we are choosing the frequency of this band pass filter as a IF frequency, so that it will pick up the IF frequency component, which is also purely sinusoidal signal. So output what we will get an FM signal of IF with IF carrier frequency. So, or you can say IF carrier modulated FM signal, but here the amplitude will remain constant because of the hard limit used at the detector. So now the FM receiver will looks like this. If you look at now, FM receiver will looks like first is a IF carrier filter. Then these four terms are basically detector term or FM demodulator term. This first block is known as, if you look at here, this block is known as basically limiter, because we are using a hard limiter followed by a band pass filter. Then another block is known as FM discriminator. The differentiator and envelope detector are known as FM discriminator, and the hard limiter and band pass filter are known as limiter. So there are two parts of a FM detector: limiter and FM discriminator. And the last part is as usual baseband filter. And so now with these blocks, we'll start analyzing the effect of noise in an FM system. Here, the FM signal plus noise is added. If you look at what is input signal is equal to A cos omega ct plus K, this plus NT, noise NT we are adding, and whose power spectral density is zeta by 2. Now S1T is the signal at the output of the IF carrier filter, and S2T will be the signal at the output of the limiter, and here S3T is the actually here I make a, actually here I can say S2 dash, the output of the you can say S2T. Here also I can say S2T is the actually output of the limiter, and S3T we should not consider now this as S2T. Now S3T actually we can say that this is the signal term only at the output of the differentiator. Then this output of this differential will pass through the envelope detector, and this will be the S4T. Output of the envelope detector, we can say the signal is S4T, and output of the baseband pass signal is known as S0T. Similarly, we can calculate a N1T, N2T noise at a different point. Another two things here we have to consider here, that is, this is the actually IF filter frequency characteristic. We are assuming that IF filter here in this analysis, we are assuming ideal band pass filter, centered at frequency fc, and the bandwidth is equal to twice, if you look at del f plus fm, or you can say twice beta plus 1 fm. That is the bandwidth of our FM signal. So this IF filter bandwidth is equivalent to the bandwidth of our FM bandwidth or signal bandwidth, FM signal bandwidth. Similarly, if you go through this HF, there is this frequency FM discriminator. The characteristic looks like this. That is frequency versus magnitude. If you look at that, is a linearly proportional. So if frequency will vary, then based on that, this will proportionate output of voltage it will get. So this is a frequency selective network. You can say frequency discriminator or frequency selective network characteristic. But when we'll go for the evaluation of the signal power, first what we will do, we will first calculate the signal power at each and every stage. Stage by stage we will calculate the signal power. Then finally we will get the output power of the output of the baseband filter. Similarly, also we know the power spectral density of the input noise. Then at a different then we have to calculate the power spectral density of the IF filter, then the differentiator, then the baseband filter, or we can say low pass filter. So that's why first we will go for the signal power calculation. So what is our signal? Input signal. We are not talking about noise. Let us assume noise is 0 in this case. To evaluate the signal power, let us assume noise is equal to 0. So that's why this S1T. S1T is the actually, if you look at, I can say that is also SIT, the output of the my IF filter signal is also equal to the output. If you look at output of the IF filter is also equal to the input filter. Here in this case we are assuming for the signal case, because we have already assumed that the bandwidth of the IF filter is equal to the bandwidth of my input FM signal. Therefore S1T we have assumed that S is equal to SIT, and that is equal to the, if you look at, this is the signal, that is AT cos omega ct plus k omega 0 t dc. But here, because this AT is varying, here we are assuming that the noise is present there. So in this case you have considered noise because it is a variation. So now after limiter, what will happen? After the IF filter, there is a limiter. So it will fix that value. So this L is the, actually L is the limited value of the limiter. So it will limit that amplitude. It will fix that amplitude. The amplitude variation will be constant now, which will be L cos omega ct plus k0 t mt dt. So now the output of the limiter, we can get an FM signal having a constant amplitude L. So now we will pass this signal through a differentiator, because after limiter there is a discriminator, which is a differentiator and an envelope detector. So differentiator out, if you look at differentiator output is equal to S3T. So if you differentiate this signal with respect to time, then we will get this signal, which is an AM plus FM signal. Then once we will pass this signal through a envelope detector, only the envelope part will appear at the output. So we can say this is with the output of the envelope detector. So minus AL omega C plus KF into MT. So we can write that minus AL omega C minus AL KF MT. So now S40, the first term, if you look at in S, and that is S40, signal X40 or equation 7, this is a constant amplitude, and this frequency, carrier frequency, which is here is a IF frequency, is also constant. So this term is a DC term, which will be blocked by the baseband filter. Baseband filter basically blocks the DC term. So only the output of the baseband filter will be this. So now once I will get this, we can assume that this AL is equal to alpha and KF is equal to K. So that's why S0T can be represented as alpha K MT, and L is replaced by alpha here. So the output power will be now S0T, that is equal to output power is equal to, what is that, mean square. So if you look at mean square value, is my power. So I will take the mean square value. So mean square value is this alpha square K square, because they are constant, then M square T bar, or you can say expectation of M square T. So this is my power, or our power, signal power at the output of the baseband filter. Clear? So here we have evaluated the signal power at the output of the FM demodulator, or output of the baseband filter, you can say. So now we'll calculate the output noise power. For this, we know that this received signal is a noise mixed FM signal. So now, if you write, or we can say, because we want to evaluate the particularly noise power at the output of this receiver, therefore we can assume also that, let us assume that the signal which is actually we are receiving is the only carrier signal. How will you get a carrier signal? Only if you assume that the modulating signal is 0, then automatically the FM signal will become a carrier signal. So now we are assuming a carrier signal, or we can say FM signal is not modulated, or we can say FM signal is with MT is equal to 0. So then the input signal plus noise arrived at the IF filter will be BIT, that is equal to, because this MT is equal to this term is equal to 0. So therefore only one term will be SC cos omega CT, another term which is a noise term. So carrier term plus noise term. But for the simplicity, we are assuming, most of the time we are taking assumption to simplify the procedure, or to mathematical tractability or mathematical simplicity. We are taking this assumption. So now, which can be represented as, if you look at this noise component NT is represented as NCT cos omega CT minus NST sin omega CT. This noise, if you go to the mathematical representation of noise, then there is also quadrature, and in phase and quadrature component of noise. Quadrature components of the noise also there is a representation. So noise NT can be represented as two parts, NC and NS. So NC and NS are the quadrature component of noise. So how will then, if noise has a power spectral density of zeta by 2, because we have assumed that noise NT is white Gaussian and the power spectral density zeta by 2, then this quadrature component noise NCT and NST are also white, because NT is white, so quadrature component noise is also white, that is NC and NST are also white, but the power spectral density of NCT and NST is equal to zeta, 2 times that NT. So with this condition, now we can represent this VIT is equal to carrier component or signal component plus this noise component. Correct? See, this noise component we are here, this is the only one point we have to note here, that in this noise analysis, in noise in FM, we are representing the noise in terms of quadrature component, and this quadrature component of noise are white because NT is white, but the power spectral density of these quadrature components are zeta rather than zeta by 2. Now, if you look at this quadrature component of noise, the previous equation, because there are, if you let me go through that previous equation, then you can understand this equation. If you look at this equation, this is A cos omega CT plus NCT cos. So there is a cos term here, another cos term here. So if you take the cos term common, then I will get A plus NCT cos minus NST sin. So therefore, in this case, we can also simplify this equation number 11 as like this, that is a plus nct cos and minus nst sine omega ct. Then if you look at and if you represent this, because this cos and sine are orthogonal to each other, so that's why this magnitude a plus nct is in this x direction. nst can be represented here. It is minus is there. nst should be sine. Actually, sine term is here. So minus sign is this side. This side is minus sign. So therefore, minus term. So that's why I can write nst here. Now what will happen? The resultant vector, look at here. This is the resultant. This I can say r of t. So this r of t, the resultant, is equal to this a plus nct square plus nst square root over. And this a plus nct I can write rt into cos theta t, and this nst can be written as rt into sin theta, because the projection of rt on the x-axis is rt into cos theta t, and projection of rt, the resultant vector on the y-axis gives nst, that is rt into sin theta t. So therefore, a plus nct can be written rt into cos theta t, and nst can be written as rt sin theta. Therefore, this equation now we can represent in terms of rt, that is rt into cos theta t into cos omega ct. This term will be replaced by the term rt into cos theta t here, and this nst term is replaced by rt into sin theta t term like this. So now this, if you look at this equation, this is a like cos theta, cos a into cos b minus sin a into sin b term. So that is a cos a plus b term. So now this term, because rt is constant, if I take common, this rt and rt here be common, then this cos a into cos b and sin a into sin b term. So therefore, this equation can be represented as, so input signal now, that is Vi or V1t, can be written as Rt cos omega ct plus theta t term. Look at here. If you remember that we have assumed noise nt there, but we have assumed information is zero, empty is zero there. But now, without information, message signal empty, the input is not an FM signal, it is a carrier signal. But look at here, when noise added, and we have used the quadrature components, it looks like this amplitude variation. They look at it, the amplitude is not constant, it's varying amplitude, time varying amplitude. And the second, this term, second term, there is an angle theta t, and this theta t is actually our noise term, because if you look at theta t is equal to, if you look at the phasor diagram, NCT and NST term, that is the angle between the A plus NCT and RT. So that is the angle. So output of the limiter, now it will pass this signal through a limiter. Naturally, the amplitude will limit to certain level. Here we have assumed the same amplitude AL. So this RT will be limited to AL. Now the equation 16 will reduce to AL cos omega ct plus theta t. Let assume high input SNR. First we will assume high, again same thing, let me again tell you that when you are assuming something to make the mathematics simple, or you want to simplify the formulation. So that's why when you use this, that assume high end signal to noise ratio, input scenario is very high, then NCT, look at here. Naturally, this is the signal part, and this is noise part. So because we are assuming the high SNR, that is signal power is much higher than the noise power, then only the SNR will be high. So therefore, the magnitude of NCT, as per with this assumption, we can say the magnitude of NCT will be very, very less than the amplitude A. Here A means actually AL, we are assuming AL is equal to A. Here L, if we'll assume AL is equal to A, then we can say that is equal to A. Correct? We can assume like that also. That's a constant value. So at the same time, these two components, that is quadrature components of noise magnitude, are very less than A. That is the meaning of the high input SNR. With this assumption, what is the tan theta? Because if you look at tan theta in the previous phasor diagram, that is NST by A plus NCT. Because that diagram, if you recall, that is this side is A plus NST, and this side is this is A plus NCT, and this is NST, this side NST. Correct? And this side is A plus NCT. So this theta resultant vector is like this, and this vector, if you look at this to this, is equal to theta t. So that's why this tan theta t is equal to NST divided by A plus NCT, and which is equal to, we can write NST by A, because n magnitude of NCT is much less than in comparison to A. So if it is much less than the value A, then we can neglect this. With this assumption, with this condition assumption, we can neglect this NSCT. So therefore it is approximately equal to NST by A. So this is only to simplify the calculation of noise power. Then we will go to theta t, that is equal to tan inverse NST by A, because again the same condition, because NST, the numerator is much smaller than the denominator. So the total term will be very, very less, or it is very close to 0 or very less. In that case, tan inverse theta is equal to, or x is equal to x. Tan inverse x is equal to x, because sine theta, if theta is very small, then it will be theta. So that's why you can write this is the value. So now tan inverse this term will be Na equal to NST by A, because of the very small value NST by A. Now V2T, now we can write that V2T. V2T is the actually, what is V2T? V2T is the output of the, you can say, limiter. So that limiter, the equation 17, can be written as, because this theta t, now we expressed as NST by A. Now we replace this theta t in 17 as NST by A. So if we replace that, then it will be V2T, again written as AL cos omega ct plus NST by A. That is equation 21. So output of the differentiator, now this equation 21 will pass, or you can say it will be the input to the differentiator. The output of the differentiator is V3T, that is equal to minus L omega C plus L by A dV by dt NST sine omega ct plus NST by A. So output of the dye detector V40 is equal to the envelope. So this envelope will get detected. I did a mistake here. Actually here this A which we are actually, this is L the amplitude limiter, but this A is the input amplitude of the carrier signal which we have considered here. That is not the same. We should not say that is same. That is actually here. This is the A. And this A comes from the, actually if you look at input FM signal with a MT is equal to 0, we have assumed that is the, this is the actually A, this A cos omega ct. Here AC, the carrier amplitude is AC, that is equal to A. So that A is the carrier amplitude, L is the, actually L is the, you can say, the amplitude limiter output maximum value. So please change this, that is AL is not equal to A. So therefore, now when we will go for the envelope detection, then we will get this envelope output of diode detector is this, but this is the DC term. Again, this is a DC term, it will be blocked by my baseband filter. So I don't bother about this, only I bother about this. So what is my objective now? My objective is to if you look at what is the power spectral, we know the power spectral density of NST, which is zeta. What is the power spectral density if I pass NST to a differentiator? So therefore, if the power spectral density is zeta, then power spectral density of these two terms are this ratio is a constant value. So that is not a problem. Only here we have to evaluate the power spectral density of d by dt NST, and which will be actually input to the low pass filter. So how will calculate? Because we had gone through that, the power spectral density of a differentiator is equal to output of the differentiator is equal to h of a mod square into input power spectral density. So differentiator transfer function is equal to j of omega. So that h of a mod square is equal to omega square. So I'll get omega square. Look at here. And zeta is the power spectral density of this, and this AL by AA will be squared. So this power spectral density square of this term plus the h of f mod square, that is omega square, because differentiator transfer function is equal to j of omega. J of omega mod square is equal to, if you get, then that will be omega square. And NST is the power spectral density of zeta is the power spectral density of NST. So that is equal to alpha square by a square and omega square zeta. This is equation 24. Now once you calculate the power, noise power, then Gn for F, output power spectral density, is equal to, what will happen? This is the input to the my low pass filter. So input to the baseband filter, because this is the output of the, you can say, diode detector. So this power spectral density will plot, then this will be looks like a parabolic kind of thing because of this omega square. This is F. This frequency power spectral density is a plot of frequency versus the power. So this is the power spectral density. You look at here. This is the parabolic surface. This is the power spectral density of, you can say, input noise to the baseband filter or output of the diode detector or envelope detector. So when you pass this through the baseband filter, then baseband filter frequency is equal to FM2 minus FM, because it is a two-sided power spectral density. So only this to this power spectral density will pass, because that is ideal. We are assuming gain is equal to 1. If we are assuming the low pass filter characteristic like this, that is a constant FM2 minus FM, and we will pass this kind of power spectral density through this, then only we have to find out the area between minus FM to plus FM. That area is our output of the baseband filter. So now this is my noise power calculation. That is the area of that GN4 we have to find out between minus FM to plus FM. So this will be minus FM to plus FM. This term we have to calculate. If we'll go through this, simply we have replaced this GNFR value which we have evaluated there, that is alpha square zeta by a square, and then omega square, there is a term because we have to integrate with respect to f. So omega square is a frequency value. So that's a omega square df. So once you calculate this term n0, this term, we can expand this omega square is equal to 4 pi square f square df. So 4 pi square f square df, that total value is equal to n0 is equal to 8 pi square by 3 alpha square zeta a square fm cube. So noise power is equal to, these are the constant, 8 pi square 3 alpha square a square, zeta is the noise part, and there is a frequency. So if you look at FM is my frequency. If the signal bandwidth will be increasing, then also noise power also be increasing, because this baseband filter bandwidth depends upon my signal frequency bandwidth. So that's why it depends upon noise power, also depends upon my message signal bandwidth. So therefore we can write the signal to noise power. The S0 already we have calculated, that's alpha square k square m square t bar, and N0 is equal to, now we have calculated equation 27 that we have put here. So the total, if you look at simplify this, then this would be 3 by 4 pi square k square m square t bar by fm square into a square by 2 uh, a square by 2 by zeta fm. We knowingly we have written as zeta fm here because input power term we want to mention this. So this is actually, if you look at the initial case, the signal power, I can say SI, a square by 2 is equal to input power, and zeta fm is also known as input noise power. This is input signal power, input noise power. So knowingly as in noise in AM we have discussed the a square by 2 and zeta fm, all these term we have used as signal power and noise power. So therefore this if mt is a sinusoidal and frequency domain deviation is delayed, then this SIT, the input signal power, can be written as a cos del f by fm, this sign term. Already, if you look at the fm equation, this is fm equation, and this is my beta term. Modulation del f by fm is my modulation index. So now, then kmt is equal to, I can write kmt term. This kmt is equal to this term, that is equal to 2 pi, because this kmt term, because this is my mt. If you look at the previous equation, that AC cos omega ct plus k integration of 0 to t cos 2 pi fmt, cos 2 pi fmt, then if you look at that, this k term is nothing but this 2 pi del f term it will come. So that then k square m square t bar is equal to 4 pi square del f square by 2, that is equal to 2 pi square del f square. This is the total power we are calculating there. So replacing this value in the SNR value, we can get S0 by N0 is equal to 3 by 2. Simply what we are doing, this k square m square t bar, we are replacing in terms of the frequency deviation. So that this equation again in terms of frequency deviation as the input noise power and output noise power. So that's this a square by 2 is the input signal power, and zeta fm is the input noise power. So this is the zeta fm. And this del f by fm, we know del f by fm is equal to beta. So directly we are writing 3 by 2 beta square si zeta fm. So it is observed that if modulation index beta increases, then SNR increases. So wideband FM, if you look at beta is very, very large than 1, and if you increase this beta, then automatically the signal to noise ratio will also increase. So beta, if will increase, then also signal to noise power is increasing. But at the same time, when we are increasing the beta, the bandwidth of the FM signal also increasing. So it is not always the same, because there is another term we will go through in the next class, that is a trade-off. So that is not the only, because when you're increasing the beta, that means the bandwidth is increasing. Then when the bandwidth is also increasing, then more amount of noise will also enter. So at a point, there is a threshold. At that point, this the amount of the SNR actually in terms of the beta increasing, it will start decreasing. So in other words, as the bandwidth B is proportional to beta, if bandwidth increases, the SNR decreases. So now we'll go for the figure of merit of the FM signal, that is gamma, that is equal to S0 by N0 by SI by NM. But SI by NM is equal to A square by 2 divided by zeta FM. So that term if will cancel in that term, because we want to divide the SI by FM. To find out the figure of merit only, we have expressed here the output SNR in terms of the input SNR. So that's why when you go for the figure of merit, if you divide the input SNR, then only you will get 3 by 2 beta square. So this figure of merit, if you look at the figure of merit, that is equal to, in FM system, that is equal to 3 by 2 beta square, or we can say 1.5 beta square. We'll compare the FM and AM signal. That figure of merit of AM is equal to M square by 2 plus M square. What is AM is the modulus index, and the maximum value of AM is equal to 1. Therefore, if you condition the maximum value for AM is equal to 1, then figure of merit is equal to 1 by 3 for the AM system, for AM is equal to 1. And for FM system, for if you look at beta is always greater than 1 condition, we will consider. Then even if you look at beta is equal to 1, if you consider also it will 1.5, which is much higher than the AM signal. So that's why FM system is better than the AM system in the presence of noise, because figure of merit in the with the modulus index is equal to 1, also 1.5, there 0.33, which is very high. And for wideband FM, again, if you consider, then naturally beta is greater than 1, so that's why it will be much greater than 1.5. Therefore, FM has a greater SNR over the AM, and the figure of merit gamma FM by gamma AM is equal to 9 by 2 beta square, or you can say 4.5 beta square. For FM, bandwidth is equal to twice beta plus 1 FM. So that's why it will replace this term beta. If for beta is greater than 1, naturally we'll go for nominal bandwidth, not Carson's bandwidth. So beta if greater than 1, very large than 1, then we can neglect this 1. So naturally this bandwidth of the FM is twice beta FM. And if we'll go to the beta value is equal to beta FM by 2 FM. So I can write beta FM by 2 FM. What is 2 FM? If you remember the 2 FM is my AM bandwidth. So this if you look at, we can say modulation index can be represented in terms of bandwidth of FM and bandwidth of AM, that is BFM by BAM. So now therefore the gamma FM by gamma AM ratio is equal to 4.5 BFM by BM square. So thank you. So any question, you can go through my Google class, and already there are assignments. You can upload the assignments, and then if you any doubt, you can also mail me my mail ID. Thank you. Thank you very much.